Hey, what's up? It's Jake from Newest DevOps, and we're going to talk a little bit about Kubernetes components, as well as Conway's law and some promise theory. So, before we get into actually building stuff, we want to understand what it is that we're doing. So, I'm going to start out by talking about Conway's law. So, Conway's law states that organizational design systems, like like that you would design a system to mirror your own communication structure. So imagine like in this diagram that you have these three different nodes, and they manage pods that, and we'll get into what all that means, that do different things. So you have like a database, and you have an application, and you have an API. Well, if the communication structure is such that you have a team that, or a person or whatever, that manages each of these entities, then these entities should be separate and managed separately, and so that your cluster would be architected or designed in such a way that it mirrors your organizational structure. So if you have a full stack developer, you're likely to have a full stack of application containers. Whereas if you have that broken out and you have a developer team and you've got an operations team, um, you may have different layers in your organization, and therefore Conway's law would say that you should have different layers in your application. Um, the reasoning behind this is that in order for a product to function, the authors and designers of the parts have to communicate with each other to ensure compatibility between components. So the technical structure of the system reflects the social boundaries of the organization that produces it. Um, and the communication can be a little bit more difficult. So complex products end up looking like the organizational structure that they're designed for. Um, Mainly, this law is applied in the field of software architecture, but Conway did direct that it can be more broadly assumed and applied to most technical fields, which I think is true. Um, so it's important to understand Conway's law when you're looking at design, because a lot of times, if you have two organizations that do not communicate with each other, and you have containers representing the work that those organizations complete and deploy, and the containers are communicating with each other, then it would stand to reason that those teams should also be communicating with each other, since the two parts of the stack are interacting with one another. So um, there may be implications where one app is having an impact on another app, and so those teams should be discussing that. So, social boundaries and software architecture, this is something that a lot of people, computer scientists, would push and advocate for. But in practice, I don't see enough of this. So it's important to understand that Kubernetes design, as you know, I just finished watching part one and part two of the Kubernetes documentary published by Honeypot. They specifically mentioned like that was the intent behind that. The other thing that they talked about was promise theory, and that um, in the context of information science, the promise theory is a model of the cooperation between agents who publish their intentions to one another, and those intentions are called promises. So, this is a labeled form of graph theory that describes discrete network of agents joined by unilateral promises. So, in the case of a promise, it's like, this is my intent, right? And my intent is to, um, the whole purpose of the intent is to increase the recipient's certainty about a claim of past, present, or future behavior. So, think about like configuration management, when it's like, this is my past behavior. This is what I want the future behavior to look like, and um, I want you to make me a promise that this is what it's going to look like in the future, and then it will return a response to keep that promise. So for a promise to increase in certainty, the recipient needs to trust the promiser, but trust can only be built by the verification that promises have been kept, just like a regular person would have building trust with another by another person keeping their promises. And in this case, it's a symbolic relationship, right? So each agent assesses its belief that the promise, outcome, or intent will be kept, and then um, the goal is to basically offer a model that unifies the description of an information system with its intended meaning, which we would call semantics. So that promise theory is also an important part of Kubernetes because everything in Kubernetes is based on promises, which we'll get into. So before we start getting into um, building things, we want to make sure we understand what is going on and how it works. So those are two concepts we wanted to cover. And now that we've gone over that, let's take a look at the Kubernetes components. So when you deploy Kubernetes, you get a cluster, right? Here's our cluster, this big gray area. This is all the cluster. You'll have worker machines, right? These are your nodes. And the nodes will run containerized applications. And every cluster, right, this gray part, has at least one, what we call a worker node. The worker node hosts pods that are components of the application workload. And then you have this control plane that manages the worker nodes and the pods in the cluster. So in prod, the control plane usually runs across multiple computers, and a cluster will run multiple nodes, so you have some fault tolerance. But let's get into a little bit more about what all of this is. So the control plane components make decisions about the cluster. So like, when do I do something? How much of it do you need? Et cetera, et cetera. It also detects failure. So if something is failing, it will make sure that it's started, or if it can't start, that it's replacing something. It can run on any machine. For simplicity, it says setup scripts typically start all control plane components on the same machine and uh, don't run user containers on the machine, which makes sense, right? It's like the control tower. So this control plane will be on like one machine, and then you'd have a worker node on another machine, at least one, and then other worker nodes on other even more machines. And you can create highly available clusters. Um, and we'll get that's and this gets into a little bit more technical details, so we're not going to quite go there yet. So let's talk about what you have in here. Okay, you can see 5 different pieces. Excuse me, I'm tired. You have the Kube API server. So the API server is a component of Kubernetes control plane, and it exposes the API. So it's basically the front end, right? So this is how you interact with it. The main implementation is the Kube API server, and it's designed to scale horizontally by deploying more instances. And you can run several instances of the Kube API server and bounce traffic between those instances. So if Kubernetes, your cluster is getting a lot of requests, and the requests are all interacting with the API, then what will happen is more of these can scale horizontally to make sure that it can manage whatever traffic you have coming in without any issues. So the next part would be etcd, and this is the key value store. It uses to store the data for the cluster. And if you're using etcd, you need to make sure you have a backup plan. And so we'll look at doing backup plans. So this is where our key value data store lives for this stuff. Think of it like state. And then you have a scheduler. So the control plane watches for newly created pods with no assigned node and selects a node for them to run on. You can think of this as kind of like auto scaling, but it's also kind of like target groups and things like that in AWS. So it'll take into consideration like, what are my resource requirements? What are my hardware constraints, etc., whether it needs to be specifically located in or whatever. And then we have a controller, and you've got the Kube controller manager, and then we got the cloud controller manager. So the control plane component that runs the controller processes is the Kube control manager. And logically, each controller is a separate process, but to make it simpler, they're basically just all compiled into a single binary and run as a single process. So this would include, controlling nodes, jobs, endpoints, tokens, etc. Whereas the cloud controller manager is a little bit different. And this embeds cloud-specific control logic. so that you can link your cluster into a cloud provider API and separate out the components that interact with the cloud platform. If you're doing it on-prem or like in a Raspberry Pi or something, it doesn't have a cloud control manager, which makes sense because it doesn't need one, right? And just like the Cube Controller Manager, it combines everything into a single process, so you can scale it and make it be fault tolerant. And this would be your node controller, your route controller, service controller for deleting cloud provider load balancers and stuff. So these are all the components of your control plane. And then your node also has some components in here, and you can see a kubelet and a proxy, right? So let's take a look at what is that. So the agent that runs on the node of the cluster is called a kubelet. And that makes sure that containers are running in a pod. The kubelet takes a set of specs and provided through various mechanisms ensures the containers described in those specs are running and healthy. So this is like your state, right? So like I know on this pod, I'm supposed to be making sure that uh, these are running, and it acts as like the hall monitor to be like, "Ooh, hey, this isn't running," and then it'll tell the API server, which communicates to the scheduler, and the scheduler goes, "Oh, then go ahead and create more." It doesn't actually manage the containers that were not created by Kubernetes, so it'll only manage the ones created by Kubernetes. And then you have the proxy, and that's the network proxy that runs on each node that implements part of the service concept. And so basically it just maintains all of your network, right? And it allows you to communicate with each other. It uses the OS basically for packet filtering if one is available. And if it's not, then it just forwards the traffic itself. And then you have your container runtime. So the runtime is the software responsible for running containers. So Kubernetes supports Containerd, CRIO, and then any other implementation of a CRI, Container Runtime Interface. And you can see here, like, well, what is there to use? And you can see that you've got these different. Here's 5 of them right here. Um, they're talking about Docker, CRI integration, etc. So you need to make sure you're using something. I'm not sure what I'm going to use yet, so I guess I'll just have to wait and see. There are add-ons you can add to implement cluster features. So that's something we might look into. DNS. All Kubernetes clusters should have cluster DNS. There are many things that rely on it. A web UI for Kubernetes clusters allows you to manage and troubleshoot, which is something that we'll be using. And then container resource monitoring. It has a time series database, basically, and has a UI so you can go ahead and look through all the logs and whatnot, which, bringing that up, it has cluster level logging. So that mechanism allows you to save your container logs in a centralized place. You can search and browse with your container resource monitoring and then look at the web UI for everything about that. So that is pretty much it for the components. So we're going to take a closer look at nodes, controllers, a scheduler, and then the etcd documentation before going over the actual API. And then once we've gone over that, there's a section on working with Kubernetes objects. And at this point, we don't really need to go over this because we're going to be getting too theoretical and not really understanding what's going on. So I think what we'll do is we'll go over the specific components at the bottom here so you really understand what nodes and controllers and schedulers do. And then I'll do a separate video on the API. And then once I've gone over the API, I'm going to jump back to the getting started page and then look at the learning environment to go ahead and set this up on my Windows machine. So that is the plan. If you have any questions, let me know. But if not, then welcome to the Kubernetes world.